everyone. We're really excited you came here. Thanks for attending to see us talk about all these topics. We have 4 really interesting talks, and I'm going to talk about designing optimal categories of users. And this is a problem that's super, super general. I'm sure many of you have faced it. So they're users, they're using some kind of product, and you need to come up with categories for something. It could be deciding if users are active or not active. It could be market segments like SMB, enterprise, mid-market. It could be users on Twitter and deciding what type of scientist they are, like this. So I'll tell you how to do this well. And at the end of this, I hope you'll actually think oh, this is just super obvious. Anybody would think of doing this. And if I change the way you think about doing this a little bit to kind of do it the way we did, then I think this would be a success. So we're going to get some inspiration from someone who is the author of Prior Analytics and Posterior Analytics. This is a great thinker. It is Aristotle. So he actually wrote the book on categories, where he just literally categorized every single thing that he could think of. But he was actually revolutionary because he was super empirical. He was really into logic and really into classification. So he was the first data scientist. So to kind of put this in context, put some structure. So categories are just rules. We have a rule, and we're going to take a bunch of things and divide them. So you can think of doing this with supervised learning. But the problem is, what if we don't have labels, right? In our case, we don't have categories already, so we can't do it. You could think of using unsupervised learning. So this is may jump into your head, but the algorithm that decides on the rule may have no link to the problem that's meaningful in any way. It's just a mathematical definition. So our approach, and I hope again that you think this is super obvious, is 1, decide on the purpose of your categories. And this is kind of the main intellectual leap here, which is that the categories are not something inherent in there that you need to reveal. The categories are just a tool, and you decide what you want your tool to do for you. So you come up with what do you want them to do? Then you decide on some business parameters, and these are things you talk to people in your company about and figure out how complicated can the rule be, and what do you want to do. Translate this into math, and that math should be an optimization problem, and then you solve the optimization problem, and you get the categories that are optimal for the goals that you stated. And all of these steps are hard. So we kind of started like this, our concrete problem, and this is a really stylized version of it, but we wanted to split users into 2 groups. So there's active, and we kind of think of this as they are really started their business and they're ready to actually do something, versus the ones who are not active and they're just testing, they're still building the business, and they're not really ready to go. But this is not fleshed out, right? This is just very vague. So here's some data. This is stylized data. I created all of this. So you can think of the x-axis here, these are the number of transactions that a user did. And then the total volume is the amount of dollars that they've done so far. And this is a snapshot at a particular point in time. So you have a bunch of users, they're all the dots. You can think of this as the predictors. This is kind of what we know about them at a particular point in time. Then this is the future value of the user. So we have all the users, and we've just put a histogram here of kind of what they're going to do in the reasonably near future. And this is all stuff that we care about. And the idea is, if they're active, they're about to do a bunch of this stuff. And if they're not active, they're not really going to do that much. But there's some threshold in there. We don't really know what it is. What's the difference between active and not active? And we want to make the classification based on those predictors that I just showed you here. So we could just throw k-means at the problem, and we come up with this definition. So it makes that rule. The line slices them like that, and the blue ones are the ones who have done a lot of stuff already. So we're going to say, okay, they're active. They're going to do a bunch of stuff in the future. And the red ones are the ones who haven't really done enough. But how do we know if this is good? We could also do a log transformation, do k-means, and then we're going to get a different decision rule. So it slices them differently. And how do we decide which one is better? We haven't even come up with any way to say one is working better than the other one. So we kind of went through all of this, and then we decided, well, why don't we just put structure and just say exactly what we want to do? So the intuition is there are some users that have launched their business, and we want to pick those ones out, and we want to use those ones for our metrics, so we want to filter them out of analyses to kind of clean up noise and various other things. So the idea of filtering is we want to get rid of users. Right? So our problem is we actually want to come up with a rule that classifies the least number of users as being active. Right? It sounds kind of counterintuitive. And if we don't put anything else on the problem, then we can just say every user is not active. Right? But that's not interesting. It's not helpful. So we have a second goal of the classification, which is we want to include almost all of the future activity. So you put them together, we say, we want to throw away as many users as possible, but we want to keep almost all the activity that we really care about. And so that's our problem. And we can turn it into math like this. You can write down an optimization problem. I'm not going to go through the notation, but this is what we did. So then we need to decide on some of the hyperparameters. So one thing we decided is we like linear rules, like k-means. We just don't like the k-means line itself. So we're going to search over the slopes and intercepts of a whole bunch of lines, and then we're just going to pick the one that does what we want the best. But there are other parameters in here, like I said we want to keep at least 95% of the future value of all the users, but that could be 90%, it could be something else. There's also like what predictors do we want to use? What time frame are we looking at? So I put all those aside for now, but we talked to people in the company, and we figured out like what was reasonable for that. So all that stuff was like the conceptual setup. Now I'll talk about the implementation details of how do we pick the best line out of a whole bunch of these. So we searched over slopes and intercepts. So here's a grid of all the different rules. So the x-axis is the slope, y-axis is the intercept, and then every point is a line. So we searched over thousands of lines, and the darkness shows how much of the future value is captured by the users that are counted as being active by the rule. So dark is more, light is less. And the constraint and the problem was we want to count at least 95% of the future value as being active. So that means like this region is the permissible zone. So we have to choose a solution from this zone. So if we flip the variable in the graph, so it's the same grid, but now I'm showing you how many users are being counted as active by that rule. So darker means more users are being counted, lighter means less, but we want the least number of users. So if you search over this grid and pick the smallest number, you end up with this black dot here. So that one identifies a particular line slicing through the graph that picks the least number of users as being active while maintaining at least 95% of the future value of the users is counted as active. So if we put that one onto the graph, we get this boundary. So the blue ones we're counting as active, and they've done enough transactions and enough volume together that our rule counts them as active. The red ones are not active yet. So if we put the other lines on there, we can put the two different k-means solutions, and we can see that they're not counting enough users as active to capture 95% of the volume in the future. Okay, so this compares the three of them. The two k-means ones, they capture 70 and 83% of the future value of all the users. And to get to 95%, we actually had to increase the number of users we were including. So this goes from 4,700 or 6,200 up to 8,200. So there are some caveats to this. So one, we did this in a totally deterministic way. You could think of trying to put this into some kind of probabilistic framework, but we were happy with a pretty simple solution. We did some out-of-sample testing, so we defined rules on sets of the data, checked if it was stable, did it give us the same results looking into the future. But you also need to worry about the character of the optimization problem. If you choose a really complicated rule, the problem could be really ill-behaved. You might not be able to find a good solution. And that would depend on the complexity of the rule and the distribution of the data. So you could try things like smoothing, resampling, and generally try to understand the stability of the results and like how is the problem behaving. And then there's non-uniqueness. So actually in this one I showed you, there's kind of a flat spot in the problem where there's like a bunch of solutions that are all like pretty good, and they're not, they don't give you very different results. And we actually found that when we did it in practice. We tried a few different sets of rules, and we found it didn't matter too much. We actually found that we could get a really good performance by using only one predictor. So that wraps it up, and the next presenter is Jonathan Gruhl, and he'll be talking to you about experiments. Oh yeah, so actually we have time for questions. So I'm not trying to get out of the questions, I just forgot about it. Yeah, I refer to those ones as business parameters, and they're ones that depend on like the institutional context. It could depend on your technology too. So we actually talked to people at Stripe. We had some meetings and we kind of discussed this problem, and we got feedback. It was quite interesting. We had a brown bag, and we kind of put the problem up and described it like this. And we had a group of people who said, oh, we want you to put all these other things in there. Like, we think we should consider all these weird cases that could happen. And we had other people who said, oh, this is too complicated, even with 2 predictors in there. So it was actually useful at kind of like highlighting this tension and at least giving us like a concrete thing that we could argue about. And we actually ended up going the other way and narrowing it down to only one predictor. Yeah. Sure.
Hello? Oh, cool. For your k-means, the boundary equation, I think maybe I missed it, but like you said we like linear. How do you know to choose linear versus nonlinear, logarithmic or whatnot in your specific case? Or I mean, maybe it's too simplistic to do it in that case, but how do you determine whether or not to go with a linear like cutoff or boundary?
Well, part of it is just the problem is there are kind of 2 categories, active and not active. So that if we don't do any transformations, that gives us a linear boundary. But then I tried the transformation, and the point is like we didn't really know which one was better. But as kind of like a business parameter, we decided, well, we think a linear cutoff is fine. Like we want something really simple. And there were also some other reasons behind that. So we decided like we're just going to look at linear boundaries, but we just want to find the one that does what we really want and not the one that kind of incidentally just comes up with something due to the k-means algorithm. Yeah. We ended up using the number of distinct payers that have paid a merchant. And so we have users, they're getting paid by people, and we ended up choosing if a user is paid by 3 different credit cards, like so 3 different people, then we're going to count them as like they've actually kind of launched now. And there were like a variety of reasons behind that. Like we decided we actually didn't want to choose like a dollar value based amount because in different countries, things cost different prices, and we wanted to have some uniformity related to that. And it also, it kind of rules out cases where one company just like runs one credit card a whole bunch of times for testing purposes. Because it's less likely that they're going to run several different credit cards for testing purposes. We found this has worked reasonably well. Like there are definitely cases where we don't really agree with the result, but it, for the most part, has performed pretty well. We use it for all kinds of internal metrics and analyses. There are, so in the sales context, they're very interested in how are users progressing along because they want to be very easy for them to set up Stripe and move along and get their business running. But sales users tend to have much more complicated integrations because they're bigger, they're larger companies, they're more complicated internally in terms of their organization. So often they'll do much more testing than smaller companies. And they'll end up kind of reaching this threshold before they're really ready to launch, right? Because they could do like many, many thousands of dollars in testing charges. So we're actually looking at other ways to categorize users that are coming through the sales channel. Yeah, good question. Anyone else? Okay, I'll turn it over to Jonathan now.
Okay, thanks again for coming out tonight. We really appreciate it. So you may have heard of the expression when good intentions go awry, or when best laid plans go awry. And so the meaning here really is to take in that no matter how well you plan certain projects, sometimes things are just going to go wrong. And so this is how about you try to kind of deal with experiments that might go wrong. So when we think in the context of experiments, randomization is often associated with best or optimal in some sense, because randomization provides a reliable means of creating comparable experimental groups and reduces the chance for potential biases. But experimental design can be pretty hard. And in some cases, for example, our randomization procedure may not be as random as we originally hoped. And so hopefully this doesn't result in actual fire, but it can affect or impact the way we're going to approach the data or the results. So today I'm going to talk about one such occasion at Stripe. It was an experiment around automated submission of dispute evidence. And the question that loomed over us in the aftermath was, when we fear that some aspect of an experiment has gone wrong, what can we do? And so we're going to try to answer that question, or we tried to answer that question by answering 2 more specific questions. First, given that we have some concerns about the experiments, can the experimental groups still be considered comparable or balanced? And secondly, can we obtain meaningful estimates of the quantities in which we are interested in estimating? So before I begin the discussion of experiment, analysis, considerations, let me give you a little background on disputes and evidence submission. So even in very simplified terms, disputes and evidence submission is still kind of complicated. So I'm going to try to boil it down to kind of 4 basic steps that are relevant for the issue at hand. So consider the situation where a Stripe user receives notification of a dispute by a cardholder and has the funds withdrawn from their Stripe balance. They have the option of contesting this dispute, and so they decide to contest the dispute. They can then file evidence through Stripe to the issuing bank before a deadline on why they think the charge is actually legitimate. If the dispute is successfully reversed or won, the Stripe user receives those funds back. Okay, so this is potentially a very valuable process for Stripe users. However, it can also be somewhat burdensome in that you have to decide whether to contest, you have to gather this evidence, file it before the deadline, and so it's ripe potentially for automation. And so the leads on a project to evaluate this idea wanted to compare the performance of disputes that had their evidence automatically submitted against those that did not. And so to measure performance, we considered win rate. And win rate here is defined as the number of disputes won or reversed divided by the number of disputes. And the goal is to estimate the difference in win rates between disputes with automated evidence submission and those without. So they set up an experiment where a certain subset of disputes meeting certain eligibility criteria were split up into 2 groups. Around 20% were sent to a test group where each dispute had their evidence automatically submitted. The remaining 80% were sent to a control group where evidence had to be manually submitted by the user or it was not submitted at all. So even under these conditions, we were pretty surprised when the test group win rate came back 0.16 higher than the control group. So we're done, good to go. We got a product, we can celebrate. Well, hold on there. Red flags coming out for further review. So when we did look at the randomization procedures, this did raise some red flags. In particular, we saw that the disputes were being assigned to the test group in very large batches. And this threatened the balance of our experimental groups. So now we have this concern. Has something in our experiment gone wrong? And what can we do about this? So first, we wanted to evaluate the comparability of the experimental groups. If the randomization worked, the group should have similar profiles across a range of characteristics. So we compared the 2 groups across a number of dimensions, including card type, issuer, acquirer. And one such dimension was whether the zip code was supplied as part of an address verification system check. And these checks can provide additional levels of reassurance that the person using the card is the legitimate owner. In this case, looking at the data, we saw that there was a pretty big imbalance between the test and control group. And this raises concern because the presence of this data may be associated with higher win rates, naturally. So when we looked across other dimensions as well, we saw some similar imbalances. And when we ran some statistical tests, these differences seemed to be pretty meaningful. Okay, so with these imbalances, we kind of then wanted to investigate the potential source of these imbalances. So we started to look at the allocation of disputes between test and control within individual users. And we saw some pretty interesting results. I mean, first remark that we actually have multiple observations per user. Secondly, we had 1 user who had all of their disputes assigned to the control group. We had another user who had 2/3 of their disputes assigned to the test group. Now, if we had been doing this randomization at the individual dispute level, these results would have been extremely unlikely. Moreover, to the degree that there's differences or variation in win rates among Stripe users, this is going to impact our results. So to get some sense of how this might impact our results, we selected individual disputes from each Stripe user. So we kind of set up an experimental subset, but where it's 1 dispute from each user. And suddenly we have a completely different result. the test group win rate is now slightly less than the control group. Okay, so we've been through our first question, and we've got some legitimate concerns now over the comparability of the two groups in the experiment. Okay, so now can we get a meaningful estimate of the difference in win rates while trying to control for some of these group imbalances? Okay, so to do so, we tried to model the probability of winning a dispute as a function of test group membership, while adjusting for some of these different factors like user-specific effects and dispute-level characteristics. And to do so, we used a logistic mixed effects regression model, which is pretty useful for modeling binary data where we have repeated observations from users. And so if you're not familiar with mixed effects models are named because they have both fixed effects and random effects. Fixed effects are population level coefficients. In this case, they are not the population averages, though. And random effects represent the user-specific deviations. Okay, so in this formulation, Y is our outcome, which is whether the dispute was won or lost. The test group is our predictor of interest, and we're particularly interested in the parameter beta 1, because that's going to measure how we can hope to measure the association between test group membership as well as and the probability of winning a dispute. W and Z represent our user-specific terms. And then we have this vector X, which is our dispute characteristics like card type or the presence of a zip code. And so using this model, we actually estimated then a negative relationship between the test group membership and the probability or winning a dispute. Moreover, if you look at the 95% confidence interval, it's well removed from 0, makes it highly unlikely that there's any absence of effect, much less so a positive relationship. And so when you compare this to our original result, this is a pretty stark difference, obviously, both in certainly in direction. And so this, I think this reinforces the idea that, given some of our concerns about the experiment, it's important to control for some of these differences. Now, one thing about coefficients from any generalized linear model is they're not exactly, they're somewhat wanting in terms of interpretability. And first, they're not on the response scale, and secondly, when you have random effects, there are some additional considerations. So for example, if you take regular logistic regression, you can estimate the change in probability associated with a change in the predictor variable if you hold all the other variables fixed at a given level, right? Okay, but when you've got random effects, holding everything else fixed means you need to hold the random effect fixed as well. So the individual user term now has to be held constant. This really puts pretty heavy restriction on interpretation. So instead, we decided to calculate average marginal effects for test group membership with the probability of winning a dispute. And here we saw that the probability of winning a dispute with test group assignment was actually 0.1 or 0.12 lower. Again, this is pretty stark contrast from our original estimate, both in direction and magnitude. Okay, so returning to our second question. We were able to get an estimate. Great. But there was a trade-off, right? We had to use a statistical model. We had to start controlling for a bunch of different effects, and that comes with some potential shortcomings. Maybe we misspecified the model. Maybe we omitted some variables that would have been very relevant for controlling for these group imbalances. And so this kind of feels like a partial win, because we still definitely would have preferred to use data from a successfully randomized experiment. Okay, so I'm going to leave you with one final heavily modified Winston Churchill quote. Success is not final. Experimental failures, although not ideal and certainly not without impact, are not fatal. It is the persistence to continue the analysis that counts. Cool. Thank you very much. Okay, what questions? I'll take questions. If you have questions, can you please use the mic if possible? Yeah, it's a Great question. So there were a couple of different considerations. One, I think the way they're processed, if my memory is correct, and I wasn't involved heavily with the technical details, but they're processed in batches. So the selection was easier to do by batches. However, I think there were also some issues in the timing, and that the timing intervals were somewhat irregular. So when we looked at these batches, they were heavily batches. They were pretty large batches. Also, in the way disputes are potentially queued up, I think there's some issues there that a certain user's disputes may be queued up in one group. Yes. So, okay, the question was, why did we use a mixed effects model instead of a paired t-test? I think we used a mixed effects model, one, for a couple of reasons. One, we had multiple observations on each side for the user. So if we're going to use a paired t-test, I guess we could have taken the averages from each side, but we also had some users who didn't have any observations in the other. So we would have had to kind of reduce some of our sample. Also, we still wanted to control for some other imbalances. The fact that we had these multiple observations for merchants wasn't the only imbalance that we had to control for. So that even when we started controlling for user-specific effects, we still saw that there were some differences in some of those other dimensions that we mentioned, and we still wanted to control for this. That's a great question. I do think the AA experiment would have helped, just from the standpoint that we could have seen the distribution of how the disputes were being allocated to different merchants, as well as their assignment just between the groups. I mean, we wouldn't have actually needed to see results. Just seeing the assignments alone would have raised some red flags.
I have a question.
Yes. This is unfair. You went before me. I don't get to ask you back.
Did you try any approaches based on resampling the batches?
That's a great question. So when we looked at the individual merchant, when we sampled by merchant, when that kind of in the case to see the size of a merchant effects, we did. I don't think this is exactly what you're suggesting, but we did do some like bootstrap resampling just to see whether that difference was significant. But there are definitely many other areas that we could have done it in, and it probably would have been pretty valuable. Great. Thank you very much again. So next up is Peter Lofgren to talk about some of his work on merchant fraud models.
Thanks, Jonathan. So in a lot of machine learning, the data is like more or less staying still. Like if you make a system to recognize cats, it'll recognize cats like last year the same as next year. And the cats aren't trying to fool your system. But at Stripe, when we look at fraud, the fraudsters are actively trying to fool our system and changing their behavior constantly. So you have to solve a lot of interesting creative problems on recognizing the changing behavior of fraudsters. And in the part of this talk, I'll focus on the case of dynamic fraud rates, where the behavior of fraudsters on certain email domains changes. And I'll give some tips that should generalize to other machine learning settings. So as background, at Stripe, one challenge we face is merchant fraud. Most of our merchants are good. They come here to build businesses. But some of them have stolen credit cards, made a fake website, made a Stripe account, and they just want to cash out their credit cards from innocent people. And we want to distinguish those people from people like building good businesses. And part of why this is challenging is that we really believe in a good user experience. So we want a really smooth process with like very few questions for good merchants. And we use machine learning to decide like when it's necessary to ask more questions and verify more from a merchant. So in machine learning terms, this is a pretty standard classification task to a first approximation. We're given a merchant's history, we form some features, and then we want to distinguish a fraudulent merchant who's stealing money from a good merchant who's building a business. And then the output of our machine leads to several different actions that we can take. The most common action is to accept an account. If a merchant looks good, we just want them to go on their way very smoothly and not be slowed down. And merchants can change their behavior over time. So even if a merchant looks good at first, later on they might start stealing credit cards, or we might sort of realize that they weren't a good merchant. And so we're constantly evaluating merchants to see if we should be looking at them more carefully. The second action our machine learning model can recommend is flagging for human review. we have a team of risk analysts who have a lot of intuition for what fraud looks like and what good accounts look like. For example, if someone's claims to be a barber, but they have charges from 5 different countries in the same hour, they're probably not really a barber, they're probably fraud. And humans are good at that kind of like human, like real world thinking. The third thing we can look at, the third thing the machine can recommend is more verification. We might ask someone to take out their phone and like verify that the phone number is theirs. And for a good merchant, this is pretty easy. They have to fill it out in like a few seconds and be done. But for a bad merchant, if they're trying to create lots of accounts to get like fraud in parallel before we detect them, they have to get a bunch of phones and like burn through them, and just slows them down. We try and choose interventions that are pretty easy for good merchants, but like annoying or like time-consuming for bad merchants. And finally, the most extreme option is to block merchants. We only do this if we're like very, very sure that they're bad. But some fraudsters create like tons of accounts, and we need some like fast way of blocking them, so that because we have a finite amount of human time. But this is like a very high precision action. And this also leads to an interesting machine learning problem, because we really care about our recall at precision like 99.99%. And most machine learning systems aren't built for that kind of precision. But here we make that work. And our current approach to this problem is random forest. Because random forest works really well on a wide variety of domains. The features can be like any scaling. It's like pretty easy to put features in, and it handles feature interaction naturally. So it's working well for us. Someday we might do like deep learning or like more complex things. But random forest works really well, and like features are where most of the gain is at. And the first tip I'll give is to choose features that are hard to fake. This is pretty natural. But if someone, like, when people write a name or a mailing address, they can write whatever they want. And so that's not a very good feature. And like, we see them writing pretty realistic stuff. But like for bank accounts, if they write the wrong bank accounts, like they don't get their money. And so they have to write real financial information. And like the email address is verified, so that's to be real. And we try and focus on these real features and make things that will work sort of in a more long-term system. And now I'm gonna describe 4 tips for machine learning that should be applied in lots of domains. And to be concrete, I'll focus on the case of email domains, like what email someone used when they signed up for Stripe, like Gmail or Hotmail or whatever. And I'll get to these in the talk. So as background, here's 5 email domains that people might have used. On the x-axis, I have time, on the y-axis, I have fraud rates. And we see that different domains appear over time. Like in May, like the blue one appeared out of nowhere. And this is because fraudsters notice if we block one of the domains. Like they'll use some like new domain, we'll start blocking it if it's bad enough, and they'll switch domains. And we have to constantly adapt systems to deal with different fraud rates. So when we built our system, like the first thing you might try is a categorical variable. But when we tried it, we realized that it's performing like less well than we expected. Because Scikit-learn does something pretty silly with categorical variables, so you should be careful for if you ever use it for this. It was ordering our variables alphabetically, assigning them sequential integers, then treating that integer as a real value to split on. So the splits were only available like in the alphabetical list, like the first like A through G in one half, and like H through Z in the other half, just like really silly. And the natural solution is to sort the keys by fraud rate. Or equivalently, we can just compute the fraud rate for each key and replace the variable with the fraud rate. And now we can do a split for like domains that are like less fraudy than 0.5 and domains that are more fraudy than 0.5. Or the tree can choose whatever split it wants. But it'll produce much better splits this way. Okay, so we build a system that computes fraud rates. We didn't actually build a system to compute them every night. And so the second thing to avoid is manual intervention, because someone's always going to forget to like update these things. At some point, we noticed that some email domains that we know the fraudsters are using were getting like an empty score. And this is because we hadn't updated our email domains in months. And so we did the natural thing and built a daily job that will update the email domain fraud rates. We use a system called Airflow at Stripe, which isn't perfect, but works pretty well. It can run every night, and it also handles dependencies well. So our like email table depends on our merchant table, which depends on a few other tables, and Airflow will manage the dependencies, like compute them in order, and then give us a nice like dashboard for how our tasks are doing. There's an open source project from Airbnb. And for email domains, like every night is fine. For some features, we wanted like up to the second updates. Like for IP address, if someone does an IP address card testing attack, they might do like 1,000 cards from one IP address. We want to know that that's happening. And so we use a system from Twitter called Summingbird. And Summingbird is also an open source project, which we've like adapted for our uses. It can take like a batch of all the like previous data, and then combine that with like the last day's data in an up-to-date like in-RAM store, and give us the up-to-date counts for email domain fraud, for IP addresses. And I also do more interesting queries, like how many distinct IP addresses has this card been used on, or like how many distinct cards does IP address use? And there's some nice data structures behind it. Because now we have up-to-date email fraud rates, and we train a model, and it looks like it's really good. Like the email fraud feature at some point had like half of all splits in our random forest were being used on like this email fraud feature when I first tried this, because it was overfitting on future data. So the problem was the following. Suppose some user Bob signs up in like January with xyz.com, and this is the first time that we've seen xyz.com. And then later on, we find out there's a fraud on xyz.com, and then like we realized Bob was a fraudster. And then today we compute fraud rates. Because we computed them today, like the fraud that we discovered in February is incorporated in our rates. And so when we train the system, we'll give it a fraud rate of like 90% across all of time, because that's like the overall fraud rate for this email domain. But now the system is like over-relying on email domain fraud rates because like, it's getting future information. It thinks they can sort of block Blob in January, even though we didn't know until February that this domain was fraudy. And also in production, this is bad because new domains happen every day, and we need a system that can handle new domains. Whereas in this like current setup I've described, all the domains are known in advance. Because in the training set, like all the domains are there. So the solution is to replay history and compute the proper historical fraud rate for each domain. So when we replay history, in January, the fraud rate for xyz.com is still like the prior. And I'll get back to say later what this means, but it's sort of like the unknown rate. And then only after we've learned, like at each point in time, will we have the correct fraud rate. So we take all the events for a domain, like which merchant signed up, and when they were judged to be fraudulent. And then we compute the historical fraud rates for each example. And now the system, when it's training, will see examples of email domain rates that have never been seen before. And it will sort of learn that like, some of them are good and sometimes they're bad. Whereas later in the training cycle, it will see rates that are like really high or really low. And it can better adapt to like new rates and be a closer like model of production. Like we always want like training to match production as much as possible. Okay, and then the final pitfall we encountered that I'll describe is having 0 or 1 for rare domains. So first, for some domains that hadn't appeared before, we were using 0 because you have to put something into the random forest. And I think the Scikit-learn that we were using didn't have support for like unknown values. It probably still doesn't. And also for like really rare domains, if you just compute the fraction, you get some weird results. Like if you have some domain that's only been seen once, that's fraudulent. Like naively, its fraction of fraud is 1/1, which is 1.0, which is the same fraction of fraud as the domain we've seen 100 times with fraud. But like intuitively, we should have a much higher score for someone who a domain that's been fraudy 100 times, the one that's been only fraudy 1 time. A simple solution to this is to have like a minimum count for email domain fraud rates. And this like works better than the naive thing. But then we get like an undefined fraud rate for people who have less than the minimum. A cooler solution is to use Bayesian statistics. We can have some prior over the fraud rate of each email domain, and then update that over time. So here in the top left, I have the uniform prior. Look at the first thing you'd start with if you didn't know the fraud rate of a domain. If we see one fraudulent example, then on the bottom left, we get this posterior. So this is sort of our like belief about the distribution of the fraud rate of this domain after we've seen one fraud rate. So the x-axis is the possibility of a fraud rate, and the y-axis is the probability of that fraud rate being the true fraud rate. And after one fraudulent, we know that it's not 0. So like the probability of the fraud rate being 0 is 0, but it's still like a lot of uncertainty over what it really is. On the top right, I show the posterior if we have 10 out of 10 fraudulent examples. And we see that now like the posterior is pretty confident that it's a high fraud rate, like as it should be. And it can also handle like mixed results. If you have like 10 good results and 10 bad results, you get the bottom right posterior. And now like it's sort of learning that the mean is close to half. It's not clear if it's 0.4 or 0.6, but it's pretty clear there's not like 0.1 or 0.9. So to feed this into a random forest, like it's sort of hard to feed in a distribution. And so we just collapse it to be the expected value in the posterior. And computing that might look complicated at first. Like we have to sort of integrate over all possible parameter, like find the probability of that parameter under our like prior, find like the probability of the data under that parameter. There's a lot of like Bayes rule stuff we could apply. But if you look through the math, it's really beautiful. The computation you get is equivalent to the following. You add one extra good example and like one extra bad example and compute the naive ratio. And that gives you the posterior if you have the uniform prior. So going back to our example from earlier, if you have one bad example, your posterior expectation is 2/3. Whereas if you have 100 bad examples out of 100, your posterior expectation is 101 over 102. And now we've captured this intuition that the more fraudulent examples you see, the higher score you get. And also we don't have like empty variables now. Like if you have no examples, your average is half. And as a cool bonus, you can change the prior to be like match your data better. So your data had like a 10% fraud rate. You can choose this distribution in the bottom right. And then your prior fraud rate is 10%. And this updates naturally. And now instead of like adding one good and one bad, you'll have like alpha good and beta bad. And you can sort of model whatever fraud rate you want. So in industry, there's always more things that you want to do if you had time. And two things that we might work on in this direction is first, text models. We've experimented with text models on like the product description that a user writes. And natively, you might take all the training data and produce one logistic regression, and then compute the score for all of the merchants in your training set. But now if you have some like sort of keyword associated with fraud in January that's not discovered until like March, like you don't have a way of distinguishing when you actually learned about some keyword being fraudulent. So in theory, you could like compute a new logistic regression after every new text document arrives with a merchant. And that's computationally expensive. So maybe like every month you update it. Yeah, we'll see. Another natural extension is time-weighted features. You saw in the email fraud rate graph earlier that the fraud rates change over time. And so it's natural to take like the last month or the last year and as a window, or else do some like exponential smoothing so that more recent examples have a higher weight than examples long ago. Yeah, so that's some tips on machine learning based on our helping keep Stripe free of fraud. So thank you. I can do like one or two questions. Go ahead. So the question is, have you looked at what categories of fraud are most common? So someone like we've seen people have like campaigns for like, oh, like my dog died, like please help me like get medical care for my dog, or like more like worse things than that, and like they'll have like fake like campaigns to help someone, and like it's like pretty despicable. Like I don't know, like I'm not sure what examples to use. You guys have risk analysts, we have some risk analysts here, and they'll have better examples than I do. But there's like a lot of variety in what kind of things they'll have. They'll like fake products, like fake campaigns, fake events, lots of stuff. Right, the question was about the way we get our training set is we send some examples to risk analysts, and risk analysts will label them as like good or bad. And does that like bias our training set? Is that right? Yeah. So the answer is yes, to some extent. Like our training set will be biased based on the selection we use to show the risk analysts. So it turns out to be good in the end usually, because for a bad account, eventually the cardholder will like look at their statement and be like, oh, I was defrauded. I'll tell my bank, and the bank will tell us. So eventually we do find out about all the fraud. And so most of our training set is good like for all the accounts. But in the short term, that does happen. Like the set of examples we have will be sort of biased in the algorithm's past judgments. I'll get one more question and then we'll go to the next speaker.
Hi, Peter. This is a question kind of about training set as well.
Yeah.
If you're launching in a new market that you've not been in before, or if there are markets that are particularly fraud heavy, how do you account for that bias? Geographies, let's say. For example, certain countries or certain parts of a country just tend to have more fraud.
Right. So the question is about in a new country, how do we handle the imbalance there? To some extent, we can have a variable for like fraud rate in that country. Well, that's sort of dangerous because like if we want a country to sort of like get more business, we don't want to like preemptively say it's a fraudy country. So we try to avoid bias by country. I don't know. To some extent, we can do extra manual review. Like the risk analyst will sort of pay more attention to the new country, the new area. Like we have some like new payment methods, and we'll start by having risk analysts like be more involved. And then as we get more data and like the scale is bigger, naturally we'll have machines take over for like new payment methods or new countries. Okay. Thanks a lot. So now I'll turn it over to Alyssa from my team, or from the machine learning team, who will talk about interpreting black box models.
Hello. This is the last talk, so thanks for bearing with us. So I am going to talk for a short while about how we explain the decision that a black box model has made. So from what I can tell from like going to some machine learning talks and talking to people about machine learning, many people think that machine learning is magical. I give you some set of information and you give me back a magical prediction and we move on with our lives. You know, I give you charge information, you tell me if you think it's fraud, we're done. Some people might call it a sausage factory, like something goes on in there, I don't want to see it, it's mathy, it's full of code, like I don't like it, whatever. I sort of want to take away those things and say that like sometimes there are business cases for needing to know what goes on inside of the sausage factory. So at Stripe, I'm going to talk about another sort of machine learning problem that we have for fraud. So you just heard from Peter that like we have a lot of fraudulent businesses, not a lot, but sometimes people try to defraud Stripe by pretending that they're a business when they're not. We have another type of fraud that is transaction fraud, which is when a business using Stripe is a good business, but someone has stolen a credit card and is trying to buy something. So like, I've stolen a credit card, I would like a watch, I would like a Lyft ride, etc. So we have a system in production that sort of in real time predicts the fraudiness of charges and declines ones that we deem high risk. So the magic here, we also use random forests for transaction fraud. Peter said we use them for merchant fraud as well. People care when you're declining their payments in production what that model's decision was and why the decision was that way. So business owners care when somebody writes into customer support and says, I'm not able to order food on your website, my credit card keeps getting declined. Businesses care about why we are declining like a bunch of their volume. Even if it's bad, they want to know like why we think it is bad. This is not only true of Stripe, this is true of many companies that use machine learning to actually sell something. Like people care about why a model said what it did. This actually helps us build better models, it helps us learn about systems. People care about why. So this sort of people caring about why a model was making certain decisions often motivates people to use simpler models with degraded performance. We couldn't basically take that performance hit. So instead, we chose to try to explain random forests. So I'm going to give a short overview of what random forests are, and then sort of go over how we get the explanations. So a random forest, many of you probably know, is a set of decision trees. And so this is a diagram of one decision tree. There's 3 decisions that need to be made that are in this tree. Each charge would get like 2 of those decisions made. So you basically like, for an incoming charge, would walk through this tree and decide what its fraud probability was in reality. So like we basically would separate our training set according to this tree, and it would give us different fraud probabilities depending on which leaf of the tree it ended up in. A random forest is like a huge set of these trees. Basically, like each tree would be made with some randomly selected subset of the sort of things that went into the tree. And the final fraud probability is some sort of average across the predictions from all of the trees. So the final decision, of course, is made by sending the charge through all the trees, tells you what happened, we're good to go for the what part of the question. Trying to explain why is sort of sad. Answering a customer support ticket would do something like, well, we declined the credit card because the countries were different on the, like, I don't even want to read this is really sad. So trying to explain this in a random forest with like hundreds or thousands of splits and hundreds or thousands of trees is terrible. if you use neural nets, I can't. But sometimes like people will still ask you why. I'm going to describe a solution that basically boils down to like, let's not despair. It's going to be okay. Like, let's do a simple thing and try to explain why we made the decision that we did. Let's do the easiest thing we can think of. So we actually did this. I'm going to tell you like what we did at Stripe while I've been here in the last 18 months. So 18 months ago, we had no explanations for our random forest decisions. We would like poke at the trees in a little JavaScript explorer, and it was like fun. Sometimes, not always. So some of my teammates built a system to try to explain a random forest predictions. So the first thing that we would do to try to get an explanation was actually get the prediction. Use all of the features from the charge and get its estimate of the fraud probability. Then, after we got its like original estimate, we would estimate the fraud probability by sort of taking out each feature of the charge one by one and estimating what the probability from the model would have been if we didn't know that feature. So like estimate the fraud probability if we didn't know the card brand, if we didn't know the velocity, how many times the card had been used recently, and if we didn't know like the IP address behavior recently. So we basically got these like theoretical estimates of fraud probabilities. Then we'd calculate the delta between like the real estimated probability and what we would have thought that the fraud probability was without those features. And like the feature with the biggest delta is the feature that we said would like compose the explanation. So if we were in this like little simple example, if the delta for card velocity was the biggest, we would say the reason that the model thought this charge was fraud was card velocity, or in nice English, the card has been used an unusually large number of times in the past hour. This actually mostly worked. We sort of made this up and tried it and wrote it in the programming language that we were using, and it was kind of fine. We used it internally and learned a lot about our model performance. Then came a time where we wanted to launch a product, and we wanted to expose these explanations for model decisions externally, so not just to analysts and engineers. We wanted to actually expose them to businesses using Stripe. And that is when we took a much more formal and faster approach to explanations. So I described a simple solution. We actually went to the literature and found a paper on building model explanation systems. And you can actually see that the canonical example in the introduction of the paper is credit card fraud. So that was cool. So here's what we did, which is basically comes from the paper. The first step in building a model explanation is to create sort of a list of potential explanations from a forest. So basically, take several different combinations of 2 or 3 predicates from a forest. And like the word predicate here just means any sort of question that you ask in the decision tree at any of the nodes. So like an example of a predicate is like, did the card country of issue match the country that the card was being used in? That's a predicate. So we basically create like a gigantic list of explanations based on combining 2 or 3 of these. So here's another example. This is an example of like a potential explanation. The card was used more than 3 times in the last 30 minutes, and the country of the card issue doesn't match the browser IP country. So there's 2 predicates in orange, and it forms like a full explanation. We then basically take these like explanation combinations and order them, and the way that we put them in order is by their precision. So of all of these explanations, what percentage of charges for which that explanation is true does the model say is fraudulent? So basically, if you've got an explanation that like everything satisfying that is fraud, it's like a good explanation, and a charge that comes in satisfying that, that's probably the reason. The third thing we do is make sure that we have enough potential explanations for the model to have good recall. So basically have a set of explanations that covers most of the fraud in our data set. If we're doing this project, we don't want to leave decisions unexplained if we say we're going to tell you why we made a decision. So we basically try to generate enough combinations so that we can explain most things. And then finally, the last thing that we do is basically for an incoming charge, go through the list of the explanations that we had and like return the first one that the charge satisfies. So this works. This is in production. If you have seen or used our Radar product and see sort of explanations for why Stripe deemed a charge high risk, that's how it's done. So the takeaway from sort of this process over the past year and a half that I've learned is that explaining decisions from a black box model is business critical and possible, and often sort of the easiest thing that you can think of, or even just a really simple method that somebody else thought of, works really well and is really important. So that's all I have. These are my colleagues who did the bulk of the work on explanations, and my team has integrated these into our system. So happy to take questions. Yes, the question is, in our Radar UI, we show the top explanation for why we declined a charge. Could we show 2 or 3 more? I will pass, I'll file a JIRA ticket for the team. Thank you. Yeah. So the question is, oftentimes when a random forest is fitting the split in the decision tree, it'll be something like, card was used more than 3.5 times in the past 30 minutes. Businesses don't want to hear, like, the card was used more than 3.5 times, because that sounds silly. So what we actually do is we don't really use the numbers from the predicates. We basically say, like, the feature name there from that predicate would be, like, number of times the card was used. Like, that's the name of the thing that went into the training data set. And then the sort of operator on the decision tree is a greater than. So we would just say, like, the number of times the card was used was large, and we would, like, translate that into English. We wouldn't do, like, we don't, like, expose, like, this number was higher than 3.5, mostly because, like, the 3.5 is going to be super variable and is not really sort of in the spirit of this is just a model and an estimate. So yeah, we actually maintain, like, a giant YAML file of, like, is this like which feature was it and how do we say that in English? So yeah, we don't use the, like, floating numbers.
Question here, Lisa. So if I'm a fraudster, is it possible that I can just keep trying and then understand what our algorithm is?
Yeah, that's a real question.
By you giving me information?
Yeah. So that's real. So I have 2 responses to this. The first one is, in our product, we tried to make our explanations general enough that it wouldn't be anything that, like, a fraudster would be surprised by. Like, most fraudsters know, like, if they have card cached ever, that, like, you shouldn't do it all from the same IP address. You can find this on the internet, like, pretty easily. So we try to keep them sort of high level enough that it's not, like, exposing a lot of secrets about fraud. That said, it might be a surprise that, like, oh yes, we do look at X thing when you're sending us this data. Like, this is something we consider. This is where sort of the techniques that Peter mentioned, like acting like you are doing adversarial machine learning, is, like, the state of mind that we have to be in that, like, we have to constantly keep updating things, we have to not be super specific, and, like, constantly keep retraining things to pick up new patterns. Because, like, yeah, the more we expose this, like, the more our performance is gonna degrade. Yeah.
For different models where you decide not to use a random forest, how do you determine your predicates there? Like, for neural networks, you're right, they're very hard to explain the decisions. Maybe there's a feature explanation in that case, but if you don't use a random forest, then what do you do in that case?
Yeah, so I think the paper is mostly about forests. I don't know enough about the details of neural nets to, like, specifically say if it would work or not, but my takeaway is mostly, like, try anything and see if it makes sense. like that's like basically what we did for forests at first. That was like, let's just think of something naive and use it. Like, if I were working on that problem, I would start somewhere, like, super simple and see how it worked.
Gotcha. Thanks.
Yeah, there was one question there. Interesting question. Okay, so the question was, could you, for example, use random forest to do your live predictions and use regression to get your explanation? So if you ran the charge through 2 models, one, you could just take the largest coefficient and see what happened. I don't know how that would work. I would be curious to see how many times the explanation would be, like, different, and how, like, I'm just curious about, like, if we got the explanation from a totally different model, would it even match the data that we saw? So I actually have no idea. I'd be interested in trying and, like, seeing how it worked. But yeah, the other thing is, like, if you find a nonlinear relationship or if all your variables are on different scales, I would imagine this would be somewhat challenging, but could be worth a shot.